Dean, what is it about time that we even ask the question, is time fundamental?
One of the reasons we ask the question, why is time fundamental, is because time has been so modified and messed about by recent advances in physics that we're not quite so confident that our psychological grip on time and our psychological sense of time really mirrors reality anymore. I mean, in Newton's day, the concept of time in Newtonian physics was basically a mirror image of the kind of conscious experience we have. There's kind of a flow, a river of time marching past. Events start in the future, they become present, and then they go into the past. And that was mirrored in the physics. Now Einstein comes along and says, well, actually, there's a component of our psychological explanation that isn't mirrored in reality. If you look at extreme enough scales, if you look at extreme enough velocities, then you start to see that this psychological picture falls apart. In general relativity, this gets modified even more, so that there's not a whole lot left of our psychological image of time in the description that physics gives of time. Therefore, it makes natural sense to say, well, maybe time isn't even fundamental at all. And though that it seems so fundamental in our conscious experience, which it does, it might not actually be mirrored in reality. It may be an illusion of some kind, or it may emerge from some non-temporal objects.
How can that even be possible? How can time emerge from non-temporal objects?
Well, I don't have an answer to that. And people, one of the main research topics of the present day physics is to try and work out how time could emerge from non-temporal objects. So this is why suddenly we find people from condensed matter physics and from statistical mechanics now working on things like general relativity and quantum gravity. Because in condensed matter physics, you're dealing with the emergence of order and structures of certain kinds from completely different microscopic constituents. So there might be there's some kind of role for interdisciplinarity with respect to this topic. But so far as I'm aware, there's no really decent model yet that can show you how time emerges from non-temporal things.
You followed the history of much of 20th century physics in various areas, in quantum theory and other areas. How has time figured in terms of the historical development of modern day physics?
Well, I mean, in the context of general relativity and special relativity, time becomes just another variable. I mean, in Newton's day, and well, any theory before special and general relativity, time was a kind of fixed, immutable object, something that didn't figure in the dynamical equations. It was what the dynamical equations evolved with respect to, what systems evolved with respect to.
It's a differential equation.
Exactly. But then suddenly in general relativity especially, this little t becomes a dynamical variable in itself. You have to solve equations to get this t suddenly. It's a massively radical shift. But it's a shift, weirdly, that quantum theory completely ignores. So quantum theory is based on this very old-fashioned idea where t is something that is fixed. And you need that in order to get your notion of probabilities and to get the evolutions correct in quantum mechanics. Even in quantum field theory, although you have special relativity, getting involved, you still have a fixed space-time background. You set that there, the fields evolve over the top of this thing, and the space-time doesn't care what's going on over here. So, I mean, one of the greatest challenges of recent physics is trying to get a theory that merges the two properly, so that you have a dynamical space-time and you have quantum fields on this space-time, and they're interacting.
Relating quantum mechanics with gravity, this great ambition of science today, time is a critical variable in how you deal with it.
Well, I think it's essential. I mean, it's so interesting to see suddenly how so many physicists are getting interested in conceptual issues of time and what is time and maybe time emerges. This never used to happen, right? That they would be interested in these conceptual issues. So it shows you that probably, in order to resolve the problem of quantum gravity, we really are going to have to work out what we mean by time and what aspects of time we want in a physical theory and belong in a physical theory.
What is your sense of current understanding? Is time fundamental, or is it derived from something even more fundamental?
So I think most current approaches to quantum gravity believe that time is not fundamental. And there seems to be almost a consensus forming that time is something relational. Okay, so when we talk about time being fundamental, I mean, what does that mean? It means it's not reducible to any other things. So the approach of many theories of quantum gravity is to say that time is actually composed from relations between events. Right? It doesn't make sense to speak of a property or a system existing at some instant of time. The time instant itself is something that's formed by the dynamics. You're building up instants of time by the dynamical behavior of systems, which is entirely in keeping with general relativity, the lessons of general relativity. Time isn't some background structure. You have to build it out of the equations, from solving equations and from looking at how systems behave. So the idea that time is a relational thing and space is a relational thing seems to be completely central to modern approaches to quantum gravity. Even string theory, which some might find surprising, even string theory thinks that localization in space and time is a relational thing, a dynamical thing.
And so, if that is the case, if time is not fundamental, what does that say about the structure of reality?
It says that there is something deeper to reality than the spatio-temporal world that is part of our normal, everyday conscious experience and part of all physics that we're aware of so far.